Good morning, everyone. Welcome to Brandforsk and our result webinar about modeling thermal runaway initiation and propagation for batteries in dwellings to evaluate tenability conditions. My name is Mattias Delin, and I'm the research director here at Brandforsk. And with me today, I have Johan Andersson, Chen Wang, Basude Ramachandra, and Alistair Temple from RISE. Good morning.
Good morning.
Good morning.
So, how are you today, and who are you? Can you please introduce yourself? Can we start with Vasudev?
Yes. Hi. I am Vasudev Ramachandra. I have been with RISE for 2 years now, and my background is in electric power engineering. And I am really excited to be here today to present some of the results from the project that we have done.
Yeah, you're very welcome. Yes. And Chen?
Hey everyone, my name is Chen Huang and I work as a researcher at RISE since 2015, and my focus on area is about computational fluid dynamic simulations of explosions, fires, and battery safety. Thank you.
Thank you, welcome. Yes. And Alistair?
Good morning, thanks Matthias. My name's Alistair. I've been at RISE for about 4.5 years now, since 2018. I have a background in fire safety engineering, generally in buildings, with a mix of simulation experience and design experience.
Good. Thank you, welcome. And Johan?
Good morning. Yes, my name is Johan Andersson. I work at RISE since about 2012. I have worked with simulation, CFD, most of the time, but also doing some work on fire safety of facades. Thank you very much for listening.
Thank you, welcome. Great team. We will see more of you in a short while when you will present this project that you've been doing, and then we will also have a question and discussion with you later on. A brief introduction to Brandforsk if you don't know us already. We have a vision, a fire-safe and sustainable society built on knowledge. We develop and communicate knowledge, mostly research, of course, and this is to limit the negative consequences of fire in the society. And we started in 1979, and we are a foundation since 2019. Everything that we do is funded by our supporting organizations, so they are extremely important for us, as you, obviously, and hopefully we are just as important to them. And this makes us a collaboration between many parts of society, and the funding so far is about 650,000 euro this year. And of course, we use the money for research, like this project, result communications, like webinars and other things. We also have a research school for practicing fire safety engineers, and we have scholarships for students. These are the organizations that have supported us so far this year. Thank you very much. And the fundraising is still open, and I hope that more are interested in supporting us. And of course, the fundraising for next year is also open. The program today looks like this. After this short introduction, we will have a presentation of the project. It's about 40 minutes long, and then we have time for questions. So now let's move on to the presentation.
Hi, and welcome to this webinar on modeling thermal runaway initiation and propagation for batteries in dwellings to evaluate tenability conditions. This webinar is presented by me, Johan Andersson, Chen Huang, and Vasudev Ramachandra, and Alistair Temple. The webinar is divided into 4 different parts, so I will start talking about the project, some details of the different parts, and then there will be detailed presentations on the 3 remaining scientific points. So, project details. I will start with talking about the aim and goals here. So this is what was specified in our application. So the aim is to simulate battery thermal runaway initiation and propagation using a multi-scale and multi-physics model. and compare the simulated results with experimental data. There will also be a calibration exercise in the simulations. Furthermore, there will be a short circuit simulation. So this is an external short circuit. We see how this impacts on the battery. In the last part, it's a simulation of the tenability criteria in, say, a dwelling or a location. So the gases are released from the module, and we can see how they propagate in the dwelling. So the first task was to identify data. We looked at what we had in our quite extensive database of experimental data. We identified data that we could use, and we found some proper data where we have the thermal runaways, we have the measurements of temperatures, where we can compare how the simulation and experimental development was in the experiment. So in the second part, we started building the model. We did CAD geometry of the module. We imported the boundary conditions. We could then divide the model geometry in small finite meshes. We could then see how the heat wave transferred into the module from the event. And we could see how the initiation propagated through the module with subsequent thermal runaways. And this is then compared to what was found in the experiment. In the third part, we looked at the electric simulation. We had an external short circuit. We looked at existing data. We had to look for papers where they present data on the batteries, where we could use as input for the cells. We then simulated what happens if you have a short circuit event, what happens to the module and the cells. And the last part, as I mentioned, this is a simulation of the tenability criteria. So we simulated how the gas is dispersed in dwelling, for example, and this is then compared to results from FDS, since this is a standard simulation software used by fire engineers.
In this section, I will talk about thermal runaway simulations. On this slide, it shows the battery thermal propagation experimental setup. On the left-hand side figure, it shows an experimental setup that was performed at RISE 2019, where the test data were published in a paper with reference listed here. And it's 2 battery packs over each other. And there is a live module, which is colored in purple color, and also the dummy module, which has the white color. And there is a gas burner here, and which is to there is a hole on the battery pack, and to be able to heat one of the battery cell to initiate the thermal runaway. And what the simulation model is focusing is on one of the battery module highlighted in the red color. And this slide shows the battery thermal propagation model. As mentioned in the previous slide, that each module contains 12 prismatic cells, and with the anode and cathode material with carbon and NMC, and the nominal voltage of each cell is 3.7 volt, and rated capacity being 28 ampere hour. On the right-hand side, it shows this 3D CAD geometry with a cut view. In the hash area is jelly roll, And jelly roll means it's a composition of the anode layer material and the separator layer and the cathode layer material, which is rolled in a Swiss roll shape. And then outside of the jelly roll, there is a jelly roll case, which is assumed to be having an aluminum material together with bus bar on top of the battery cases. I want to highlight that this geometry is relatively simplifications to the real geometry that is used in a test. And here is a continuation of the battery thermal propagation model. And we start with building the CAD geometry and followed with domain discretization and followed with the solving of the problem. And then finally is the post-processing to get the needed data at the needed place and also extract the figures. And this model is basically a three-dimensional finite element model. And we have to use some material thermal properties, such as for the jelly roll, which is assumed to have an anisotropic heat capacities, which means the thermal conductivity along the z-axis is much higher compared to the x and y axis. And we take those thermal properties of the jelly roll from some references. And also the cell casing and the bus bar are assumed to be aluminum material from the commercial multiphysics software GT suite material libraries. And due to the knowledge gap in understanding the fundamental understanding of the thermal runaway in the batteries, and we have to use an empirical assumptions to simulate the thermal runaway. We assume that when the temperature in the jelly roll reaches a critical value and it goes to thermal runaway, and we will release a certain amount of energy within a short time based on the previous work that is published in one of the conference paper. And here I will show this multiphysics software GT suite map. Here only part of the map is shown here to be able to better illustrate what's going on in the model. And we start with this part is a gas burner, some control logics to apply some effect on the cell casing on the small area of the cell case. And this part is a thermal runaway control logics, which will trigger, will monitor the jelly roll average temperature. When it reaches a critical value, it will release a certain amount of energy within a short time. And on all those small icons are the thermal contact conduction connections, which means the jelly roll will transfer the heat to the casing through the contact conductance. And the casing will also transfer the heat to the bus bar through the contact conductance. And also it's possible to simulate the thermal convection between the solid body to the environment, as well as the thermal radiation to the environment is also included. And here I will show one animation of batteries of this thermal propagation model, where you will see the temperature distribution through the time and how the heat propagates in the whole battery module, including 12 cells. And you will see first the initiation heating of one small hole, one small circular area, and then the heat propagation to the whole battery module. And on this slide, it shows the comparison between the simulation and experiments. And On the y-axis is the time when the cells go to summer runaway, and x-axis is the summer runaway cell number. And the open symbols are the simulations, and the filled symbols are the experiments. And also the gray areas are the standard derivations based on the 2 experimental observations. And we will see that at some locations, the simulations are over predicting, and some locations, the simulations are under predicting. And in general, the simulation is in good agreement with the measurements. On this slide, I will show some sensitivity studies. The multi-physics simulation tool is very useful for performing the sensitivity studies. And since we have many different input parameters which has uncertainties, and it's very important to understand how the change of the input parameters will affect the results. And here we have introduced a normalized sensitivity coefficients, which is defined by a fraction change of the input parameter divided by the fraction change of the output parameter. And here we focus on 2 parameters. The first parameter is the start time of the summer runway, and the second parameter is the duration of the summer runway. And here a positive sensitivity coefficient means an increase of the input parameter will increase the results, and vice versa. And we will see that the TCR, which is the critical temperature for defining the summer runway, has the biggest influence on the start time as well as the time duration of the summer runway. And also this CPJR is the specific heat capacity of the jelly roll, also has the biggest influence, big influence on the time duration of the summer runway. And the conclusion of this subtask are as follows. A battery summer runaway model containing 12 prismatic cells based on the 3-dimensional finite element approach with a combination of control logics and the empirical model of summer runaway was built using the commercial multiphysics software GT Suite. The computed summer runaway time instance versus summer runaway cell number were compared with full-scale experimental data with reasonable agreement. Quantitative sensitivity study of the model input parameters on the summer runaway were performed. The critical temperature was found to have the largest influence on the summer runaway process, and the specific heat capacity of the jelly roll was also found to have a significant influence on the summer runaway time duration. Yeah, thank you.
All right, so in this section, I briefly talk about the short circuit simulations that we have performed. Within the purview of this project, we only consider external short circuits, and an external short circuit of a battery or a cell can simply be defined as the discharging of a cell or a module through a very small external resistance. And what this basically does is, because of the small value of the resistance, there's a very large current that is flowing through, and which also implies that the current within the cell is very large, which corresponds to high temperatures. And this may or may not result in thermal runaway conditions. So this is what we are interested in when it comes to simulating external short circuits. The objective also is to model an external short circuit basically for a single cell, and to try and extrapolate it to modules or entire battery packs, and to compare the simulation results to experimental data from literature. I will also briefly talk about how the model has been set up and how the parameters have been initialized in GT Suite. And then, of course, we conclude with a short evaluation of the outputs and the related discussions. As a brief introduction, here are 3 different types of lithium-ion cells. The one on the left, or cylindrical cells, is perhaps the most popular. It's basically lower in its current capacity, and it's all the contents are enclosed in an aluminum casing. In case of prismatic cells, they are usually cells that are much higher in capacity. They are also enclosed in aluminum casings. And on the last, we have pouch cells, which is used a lot in smaller applications most of the times. These are the battery contents are enclosed in more of a pouch, a polymer pouch, than an aluminum casing. In this particular project, as it has been spoken about before, we consider experiments on prismatic cells. However, for certain data, we rely on experiments that have been conducted on cylindrical cells, and I will speak a little about that in the coming few slides. The electrical model setup is as follows. So very simply put, what we have is a single cell, which is connected to an external resistance R external. And when the current flows through the R external, what we are interested to see is how the temperatures in the cell increase, and what basically the outputs that are of interest to us is the rate of change of temperature, the rate of change of electrical parameters like the change in currents, the change in voltages, etc. This corresponds to the figure in the center, which is how it is set up in GT Suite. So you have a cell that is connected to bus bars on both sides, which is essentially very small resistances, which correspond to the resistance that is noticed in electrical connections in the bus bars that carry the current. And all of that is flowing through an external resistance, which is a set value. Now the cell is also connected via a conductance connection to a casing, which is basically the physical attribute of the cell, which is the aluminium outside of the cell, which basically contributes to the conduction of the heat from within the cell. The module itself, we know from before that there are 12 cells in the module that has been considered for simulations. So the electrical configurations are done in 3 different ways. So the first is more of a reference configuration where all the 12 cells are in parallel to each other, which means that the module voltage is the same as that of the open circuit voltage of one single cell, which is 3.7 volts, the nominal value. In the second case, it's a 14.4 volt system, which is basically 4 cells in series and then 3 of these strings in parallel to each other. And in the third case, it is 6 cells in series and 2 of them in parallel, which brings the module voltage to 22.2 volts. And all of these are nominal voltage values. Why this is done so is because the first can act as a reference configuration. The second is a 14.4 volt system, which is very close to what a standard is, which is a 12 volt system. And in the third case, it's a 24 volt system, which is also a standard in electronics. So it would be of interest to study these particular values. And we also have a common external resistance for all of them, which is 1.1 milliohms. This value is chosen because it's easy to compare it with experimental data, which they have used 1.1 milliohms as an external resistance as well. In all 3 cases, I have also indicated the current that is flowing through every individual cell. It can be noticed that with the increase in the module voltage, there is also an increase in the current per cell. This is natural because more the voltage, and if the resistance is still the same, the current that has to flow through it also increases. This is of importance because it determines the change in the rates of temperature. This is just a screen grab from what it looks like in the GT Suite interface. So in the bottom half, you see the electrical connections, which is basically all the cells that are connected. In this case, it shows 4 series configuration, which is the 14.4 volt system. And on the upper half, you see the thermal model, which basically connects the electrical model and the thermal measurements, which is measurements of the temperatures of the different casings. When it comes to inputs to the model, it can be broadly classified in 2. The first is the electrical parameters, which is essentially the nominal terminal voltage of the cell, the open circuit, which is the state of charge, which is a temperature dependent map, Similarly, we have internal resistance versus the state of charge, which is also a temperature dependent map. Then we have the cell capacity and we have the loading of the cell. So in these, the nominal voltage, the cell capacity comes from the datasheet of the cell, which is very easy to obtain. But in case of the temperature dependent open circuit voltage versus state of charge and the internal resistance versus state of charge is not something that data sheets usually provide. And hence you have to rely on experimental data. And in this case, only these two are borrowed from a cylindrical cell, since the data has not been available for the prismatic cell, which has otherwise been considered for all the experiments or all the simulations. The loading of the cell is basically when you define in the software if the current drawn is dependent on how the external circuit is connected, or if you define your own level of current which is set to be drawn, or a level of power that is set to be drawn. So in this case, the loading of the cell is set as dependent on the external circuit, so that it is dependent only on the external resistor, and it changes with the external resistance. For thermal parameters, we have the conductivity and the density, and also the specific heat of the jelly roll. And of course, we also have the external surface area of the cell, which is also from the data sheets. Here is a brief summary of some experimental results, which is very relevant to what simulations we are doing. So this is for a single cell. And here you can see that the resistance that is considered, which is in blue, is 1.1 milliohms, which is also common to the simulations that we have. So these are some very typically seen results from short circuits in lithium-ion cells of different kinds. This is just one example. And the objective was to compare this with a simple electrical model from GT Suite. We can see in figure A is basically the experimental setup from which we are comparing the results to. So it's a 10 ampere pouch cell. In figures B and C, we see that it's basically the rate of change of current and voltage with respect to time, which is also what you see in figure D. But figure D is from experimental experimental results, and B and C is basically from the results from the simulation. We see that there is an odd observation, which is after a certain time, both the current and the voltage, they saturate at a certain non-zero value. And this is something that is typically not seen in a real life external short circuit situation. Because the moment the external terminals are shorted, the current initially jumps up really high, as it can be seen in the blue curve, and then it slowly dies down over a period of time, and then it goes down to zero. And the voltage drops immediately, stays at a certain level for a while, and then the potential also drops to zero. But this is, however, not what is seen in the simulation. Similarly, there is also strange effect with the state of charge with respect to time, because state of charge theoretically can only go down to zero. But in case of the simulation, it goes down to negative values and keeps dropping linearly, which is also not the case that is seen in practice. When it comes to temperature measurements, the rate of increase in the temperature also in these cells and modules are not as expected, because you can see from literature that the temperature increase is rather exponential and not linear looking. Perhaps this can be attributed to the different input parameters to the cell, because some of them is derived from 18650 cells, which is a canned cell, and some of them are derived from the much higher capacity prismatic cells. But even otherwise, from theory, we know that for a given amount of energy released, the time that it takes for certain temperature increase is inversely proportional to the currents, which means that if the current goes up by a factor of 2, then the time that it takes for it to heat up to a certain value should decrease by a factor of 4. However, this is only in theory, and in practice, this is dependent on a lot more features and a lot more parameters than just the currents and the external resistance. However, The trend also does not match because we can see that from the lowest current configuration, which is the 1 cell in parallel and 12 of 1 cell in series and 12 of them in parallel, which is the blue curve, takes certain amount of time. There is a significant drop in the time it takes for a 4 cell series and 3 cell parallel module, which is as expected. But that difference doesn't go on to continue for a 6 cell series and 2 strings in parallel module, which is what is expected from experiments. A brief overview of conclusion and some considerations. It can be said that simple electrical modeling as it was done here is not really a very good representation of how actual short circuits in cells or batteries take place. And since this is not a good representation, it really cannot be extrapolated to modules or entire battery packs with this approach. It is highly recommended that electrochemical equations are also factored in as input parameters because a lot of internal resistance factors and the increase in temperature depends on the kind of chemistry the cell has, which GT Suite also offers in one of its packages called GT Autolion, which should be investigated. And of course, all the experimental inputs should be taken from a single cell type, which has been difficult because there are just so many types of cells. So finding all of the data that is needed to model it is difficult from just literature. So I think some time should be spent in conducting some experimental tests as well to get the data that is needed to model them. And lastly, however, all of this said, it is still definitely possible to link an electrical model to a thermal model and then to trigger the thermal runaway and do measurements in the thermal model based on the electrical model. So that is definitely possible and can definitely be fine-tuned to get better results. That's my time. Thank you.
So the third aspect of the project that I will cover now is the modeling of tenability conditions, or more accurately, the use of GT Suite to model tenability conditions. Tenability conditions are what can be tolerated and endured, and the limit is the point at which something can no longer be tolerated and endured. So tenability conditions are very much dependent on the context being considered. In this case, we're thinking about lithium-ion batteries and thermal runaway events. So the tenability conditions that we are concerned about are generally to do with the release of toxic gases from the lithium-ion batteries as they undergo thermal runaway. When we think about these gases and life safety, there can be some simple limits, such as the 2000 parts per million for carbon monoxide that's given in Boverkit's BBRAD code, or you can do more complicated calculations and consider the interactions of multiple gases, such as the fractional effective dose and fractional effective concentration methods presented in ISO 13571. So when we then want to consider how do these tenability conditions develop within the context of a room, experiments are expensive and quite hard to run. So studies in the past have often used dedicated CFD or computational fluid dynamic programs. But multiphysics suites, such as GT Suite, can have significant potential advantages over these, such as the ability to incorporate feedback loops, such like detection of a gas limit activating a cooling system that might then reduce the speed of propagation of the thermal runaway and therefore reduce the rate of gas release rate. And that can be captured in one model. However, GT Suite uses a 1D pipe network approximation for 3D shape spaces rather than actually modeling 3D CF computational fluid dynamics. So we need to assess how much this 1D simplification impacts on the results. To do this, we're going to do a simple comparative assessment with FDS rather than trying to jump straight into modeling an exact scenario. For this scenario, we're using a simple 3 by 3 by 2 meter room, which has 2 air vents to outside, so a low level one on one side and a high level one on the outside, and then a battery enclosure in the center from which the gases will be released. As we're only doing a comparative study, the actual gas is relatively unimportant. It just needs to be kept the same in both models. So we've used HCN, which has a built-in description in both GT Suite and in FDS that we're using for the comparison. The gas is going to be injected at 40 degrees C. The ambient conditions are 1 atmosphere and 20 degrees C. We also have 9 locations where we will undertake measurements. To build it in GT Suite, we need to first create the geometry for the flow volume. This can't be done directly in any of the GT Suite packages, so it needs to be created in a third-party package. So any sort of 3D CAD model can do this, or even in this case, it was very simple. So I actually used 3D modeling software for shell modeling. It can then be imported with STL into Gem3D program and converted. It's important to note that GT Suite is just interested in the flow volume and not walls and obstructions. So you need to remove these from your flow volume rather than having them specified separately as a solid within the volume. The vents are then added as pipes, which go from outside the volume into the volume. And we've also added what GT Suite calls sensors in the 9 locations where we want to measure the data. A little bit more on that later. This 3D geometry is then exported into the main model system called GTISE. And in this export process, it converts that 3D volume into a network of 1D flows, which are connected. So you end up with a simple overall model that you can be seen in the top there, where you have the subassembly, which is the flow volume, and your 3 different boundaries. So your input of your gas in the boundary flow species, and then your 2 ambient boundary conditions for the other 2. So the main model is very simple, and the flow volume has a very complex network of nodes. In comparison, the FDS model is built using obstructions with an overall 3D space. We built ours in the PyroSim preprocessor, and a visualization of that can be seen there. We've used 2 different mesh sizes, a 200mm, which matches the GT Suite model, and a 100mm mesh, just to see variation in mesh sizes and if that had a big impact. When we then go on and look at the results, we can see there are very big differences between the FDS models and the GT Suite models. The concentrations of HCN in the GT Suite model reaches 100% directly above the gas injection point, whereas in the FDS models, it only reaches a maximum of about 35%. There's also relatively limited variation between the 2 FDS models, with the main difference being the additional noise in the finer mesh. I also want to briefly talk about the GT Suite usability. And in this instance, we can see, well, you can see that the GT Suite is node-based. And so for simple models, that makes understanding it very simple. You don't have to have a large amount of surrounding model infrastructure that you can see, and you can see exactly how they all connect up to all the elements connect up to each other and influence each other. However, for complex systems like the 3D flow volume that we had in this model, the nodes can become very difficult to read, as you can see in this screenshot of part of the 3D flow volume. The other sides aspect of this is that the results are recorded directly in the individual node rather than in a separate recording device. and as the nodes don't have, the flow volume nodes don't have a physical location in their specification, so they don't have X, Y, and Z location values, but they are more defined by their relationship with the other nodes. This can make identifying exactly which node you want to record that in larger complex systems like this quite tricky. So that's why I had to define the sensors in the initial 3D model, because they get attached to an appropriate node at the right location when the mesh generation or the flow volume generation is completed in the export, and then that's how I could identify which were the right nodes. And then you need to delete these sensors afterwards, as they're used for controlling other aspects of the device, like activating valves or similar aspects that might be needed in some flow modules. And so if they don't have a device to control, this causes an error in the model and it won't run. In conclusion, there are large differences between the FDS results and the GT Suite results, and this is likely due to the 1D pipe approximation, and possibly not surprising. This approximation assumes laminar flow, and as a result will sort of favor straight-on flow at junctions to simplify it. It doesn't solve for turbulence, and so there's limited diffusion of the injected gases through the space. It's also relatively impractical to set up for large models, particularly when considering where you want to get results from and identifying the right nodes for these to be recorded at within the model setup. So it's not going to be suitable for assessing tenability conditions in open spaces such as rooms in a building. However, as we've seen in the other aspects undertaken in this project, it is quite good at modeling some other parts of battery behavior and development of a thermal runaway event. And so it can have a good role in assisting defining the gas release curves so that they can be input into standalone decoupled CFD analysis for understanding tenability conditions.
So going forward, so we have seen a few applications of DT Suite where we have done simulations of the thermal runaways with the short circuits and also the tenability conditions. So we see that this is appropriate software to be used for say designing batteries. We know that the uses of lithium-ion batteries will increase, so the demand for this kind of simulations will also increase. We also see that there is more research needed in terms of safety, but these multi-physics softwares can be a valuable tool in this design and design for safety. We see that it has good electro and thermal response, and it can also assist in computing what is the gas released from a module. And that can be inputted in CFD software, for example, if you look more closely into the tenability conditions in a dwelling. And a last point is what can be done next. So the understanding of the thermal runaway process can be done by adding the electrochemical model, for example. We can add that into the model. This is possible in DT Suite. We can also do other thermal propagation between modules and other systems. We see that we can also implement, say, something like fire extinguishment, fire barriers in the modules, and look at what is mitigation, what mitigation can look like. We see that we can also do very fast simulations where we have done explorative work with simulation. We can do modeling using, for example, machine learning to develop very fast models that can be used for then computation of safety design. So thank you very much for listening.
Thank you so much for the presentation. And now, please, all of you listening to this, ask your questions in the Q&A and we will answer them. So welcome in Chen, Vasudev, Alistair, and Johan.
Hello.
Hello.
Thank you. That's very interesting. That's a lot of work that you've done. I was curious just to understand this. The GT suite modeling of the thermal runaway wasn't really. Did you export that directly into FDS, or did you export an expression of the energy release to that? How was that done?
So in this instance, they weren't coupled, because we wanted to look at how the GT suite sort of fluid dynamics works and how good that is first in isolation, rather than trying to make sure that we were getting our export from GT suite into other aspects right, to make sure that any comparison wasn't relying on us making mistakes there. So they were isolated bit of modeling from the other aspects for the fluid flow and the tenability section. But the idea would be that if you were to do modeling like this in a real case, then you would export from GT suite. So you would take your thermal runaway, and your propagation model would give you times when each different cell goes into thermal runaway. And from there, you could then couple that with either, if you've got modeling of the cell on a chemical level, which gives you the reactions and the rate of gas release, or if you have experimental data for the type of cell that you've got on the amount of gas it releases when it goes into thermal runaway, then you can link the propagation and this data to give you an overall gas release curve, which you can input into FDS or COMSOL or whatever CFD model it is that you want to use.
Yeah.
But in this instance, they were unlinked.
Yeah.
I just want to add a little bit more comment to Alastair's comments. That actually the GT Suite is a very fast simulation tool that it simulates one-dimensional CFD. Where if your system is like a lot of pipe flows, and then it will be very efficient. You can get results in very short time. But if you are doing this gas dispersion simulation, want to discover where the concentration is more dangerous in complicated locations, then more a general purpose CFD software is better.
Yeah, exactly.
Okay, but if you, if you look ahead, if you in the future, would it be possible to couple GT Suite into the FDS, doing their calculations at the same time, getting a feedback loop from the room fire back to the battery, maybe affecting the thermal runaway with that? Is that just dreaming, or would it be possible, do you think?
Actually, it's a very good comment that actually it's already available, because it has some connections with another CFD software like Converge. Also, it's being used, for example, to simulate these conjugate heat transfer simulations. Like if you are cooling your battery module or pack by injecting the water, and it can simulate the flow using the CFD software and feedback to the finite element simulations with these heat transfer coefficients to the GT Suite, and it is coupled simulation of the combination of the heat transfer between the fluid and the solid.
Yeah, so there is links there. I suspect the processing power for doing that on a room scale might be a bit more demanding at this point in time. But I guess the speed at which computers increase in power and things, then who knows what we can manage in 5 years' time from that perspective, I guess.
Yeah, wow, that sounds very interesting, I think. Yes.
Yeah, exactly. Yeah, so it's really requires calibration. This simplified models really requires calibration with the CFD softwares, and then it will produce fast results.
Yeah.
Yes. Thank you. Well, because I know that you at RISE you do a lot of experimental work as well to learn more about thermal runaway and so forth. So it's really interesting to hear more about the possibilities to get this into modeling. And would it be possible? Yuan, you've been working with machine learning, for example. Do you think is that a possibility to add into this, and what could it be used for?
In some aspects, I think that's a really good option to build some surrogate models, for example, where you can have results almost immediately, which would allow looking at different safety solutions on a larger scale, perhaps. You can make surrogate models of cells and battery modules, for example, and then couple these into a more safety design. So I think that could be quite interesting solution.
Yeah.
Yeah, sounds good. Yeah. Your like overall objective with the project was to learn more about modeling, to be able to use it in the future to see the exposure to people in buildings where we can have batteries, like a garage or maybe a villa that has an old battery pack for the solar panels, for example. And what is your overall picture of that problem? Is this something that we need to be very worried about, or is it or more like a medium risk that we just need to be better in designing for? How dangerous is this?
That's a really good question. There can be certainly quite large effects. I mean, there have been fires initiated by thermal runaways, for example, in buildings where you have scooters or electric bikes or so that you have in your apartment.
Yeah, people love them charging near doors and things like that, because that seems like a convenient place to put them. You grab it when you go out to get your scooter. But yeah, then that when there has been risks or when there has been events that go on a thermal runaway, that's also then a very bad location to have it.
Yes.
But
yeah, of course, yes.
Knowing exactly what the risk is on a wider scale is quite tricky, because at the moment there's been a relatively small numbers of events, but enough events that we notice them, but relatively small at the same time, while the number of these batteries and things being in people's home is simultaneously increasing at quite a large rate. And so getting capturing the sort of the profile of those two aspects is on a per individual battery level, it can be quite high consequence, but maybe not that regular. But how, given the numbers of batteries that are increasing at a rate, and it's hard to know and exactly what the risk is on a sort of a larger scale. But there's two aspects, and one is understanding what that risk is and how worried we need to be, and then the other is making sure we've got suitable design tools, which this could be part of, definitely, and then allowing us to make sure that the batteries that we're designing and the way where we're putting them and things are then minimizing that risk whatever it might be.
Yeah, yeah. Because they get really, really hot. The batteries when we just get a question now. If you, for example, if you're charging a battery on a wooden table or something, can it be hot enough to actually ignite the table?
Not when behaving properly.
Not when behaving properly, no.
is I think the answer to that.
But
and then it'll be,
with a thermal runaway, it can be hot enough to actually start a fire.
Yeah, the energy density in a laptop, for example, is quite high.
Yeah.
On the other hand, it's kind of difficult to ignite a wooden table, for example.
Yeah, but then maybe if it's rather than a solid wood, it's a more lightweight one where they've got corrugated cardboard or something in the middle of them that you get sometimes, then they're going to be easier to ignite as well, I guess.
Yeah, if you have this kind of honeycomb material inside, then it's a completely different story.
Yeah. Or when people charge their computer or a cell phone in the sofa or in the bed or something.
Yeah.
Like that. We have a unfortunate a lot of fires that started like that.
Yeah, exactly. But yeah, under normal operating conditions, they won't. But thermal runaway, if you've got enough energy density, then you definitely can be a significant ignition source.
Yeah. And you also have toxic gases from thermal runaway, and you how did you work with that in the project? I know that you mentioned that in your presentation, but can you explain more about what you used and what the reality looks like and the
so in my bit of the modeling, because I was mainly just wanting to look at how limiting is the 1D approximation of the GT suite CFD, and so it was comparative, and like I said in the presentation, the exact gas used in that case isn't really so important because we're trying to do comparisons between the two models. But in reality, you get quite a range of different gases that can be released by the batteries, and it varies a little bit depending on the battery chemistry, but you get it's carbon monoxide quite often, and you get hydrogen fluoride, and can you remember any others off the top of your head, Johan? There's about four really common ones, all which are relatively nasty.
Yeah, hydrogen and also small chain carbon hydrogens.
Yeah, and then also if you go into thermal runaway, it depends on your casing for whatever your battery's in. So when we've looked at experimental ones and battery fires before, you end up getting a lot of things like hydrogen cyanide and bits and pieces and lots of metals, but quite often that comes from the car itself rather than the battery. So you have all those mixed in, and so they can be really quite toxic events. And so one of the ways that this sort of modeling and things could help out is if this gives you, because one of the tricky parts, folks, go wind back a little bit. One of the tricky parts when you're trying to do modeling of a room or a scenario and a thermal runaway event and understanding the tenability conditions is finding good data for the rate of the release of these gases. So sometimes you can find possibly the combinations which they happen in because someone's done a single cell test or something, but a single cell test releases such a relatively small amount that quite often when they're done, they're just you end up measuring the total gases released at the end, but you don't know when these are released and at what rate they're released, and that's really important for understanding how the conditions develop within a space. So that's something where this would really help with the thermal runaway aspects, and maybe the electrical modeling is you can model a whole different range of conditions under which these can undergo thermal runaway and how that propagates, and that can really help turn that sort of lumped values of toxic gases into an actual rate over a course of time, and get a few different ones, maybe for a particular battery or for a range of batteries that you might have in a situation, and then that can be put into the fluid dynamics packages to do some studies on. And it's at the moment when we come to look at, well, in situations where I've been doing modeling of battery packs before and things, and it's very much been the hardest. One of the most difficult aspects has been finding, they're not design fires, but the equivalent of design fires for gas releases, as it were, and data for that.
Yeah, because traditional design fires, they have other species of toxic gases and so forth. So we probably need more knowledge about this. And as I think you mentioned during your presentation that you have toxicity that is interesting to look in those. How much do I breathe in? But also that irritants, for example, that will make my eyes very blurry. So concentration is also important. So you need to combine those.
So from my point of view, I think would be interesting to look more into mitigation measures. If you design the module in a different way, for example, putting some kind of firewall between cells or between a number of cells to slow the event, which may be very, very good to say have a slightly longer event, you have less adverse effects, or you have longer time for egress, for example. So that there are many interesting possibilities that you can use this software for. So that would be very interesting to look more into. We have done some studies previously 6 years ago with another software and another type of cells where we built modules, and we did simulations of one thermal runaway and looked how it propagated in the module, and put then different firewalls and different say heat sinks between cells, and looked what could possibly be done to mitigate the event.
Okay, sounds interesting. Yes. And we have a question from the audience here. Will the CO detection at the very first process at the thermal runaway, will it be as good a good gas to detect, or are there some other dues? Can we detect those fires quickly enough with a traditional fire alarm, for example?
I think that it will be a better solution to monitor the cell voltages and the cell state of health conditions, and to see that's an early strategy for detecting if the cell is going to thermal runaway or not. In combination with the battery management. Maybe Vasudev, you are more into the electrical part.
Absolutely, Chen. I think I agree. If it comes to early detection, then if it has reached a stage where detectors can detect certain gases that is expected after things have gone bad, then you have certainly had enough time to detect them electrically. And in most of these battery packs or in such energy storage systems, an active battery management system is very necessary. And it's also mandatory in most of the cases. So, and it really doesn't have to be anything complex. Like Chen mentioned, just monitoring of the voltages, the state of charge, the state of health should give you enough insight into if something is going so bad that you will have a venting of these cells to detect certain gases.
That then obviously relies on you having something which it's plugged in to do so. But very, very, very much so. They're both correct. That if you're wanting early detection, you need the gas. By the time you're detecting gases, it's no longer really that early detection.
So it's better to put your money on the battery management systems and try to avoid the accident. So
yeah, and yeah, I don't know. I'm not enough of an electrical engineer or anything to know, but I don't know if these are sorts of things that you could build into chargers and all of that, so you can have alarms and things in chargers that can provide early warning that way. Vasudev?
It most certainly can, and most of these chargers do have them. For instance, since we were talking about laptops, for example, I mean, most of these systems are inbuilt into both the battery management system on the laptop side, and also if it's any of the newer versions, which is not really ancient technology, then you also have these on the charger side. So the battery and the charger are constantly talking to each other of sorts, and everything is monitored. For instance, what is the voltage, how much can it charge to, and on the other hand, the laptop knows that if the cell is depreciated below a certain value, then it's being over discharged, so you have to shut the laptop down now. So yeah, these are already incorporated, but I guess there are times when for example, some sort of mechanical abuse to these cells, or or an internal short circuit because the cell is very old, or there's dendrite growth in the cell, for instance, then there's not really much battery management system can do except for raise a few alarms, which in all situations might not be enough.
Yeah. I think maybe several layers on the battery management layers, that a good design strategy for monitoring the cell state of health and state of charge in voltage level is important. And also a second level is that when we can't stop the thermal runaway, and also the sensors for detecting the toxic gases or the temperatures or some other fire related sensors, also important. Several layers, I think it's important, not only just battery management system.
No, you need a redundancy in the design.
I think.
I mean, this is I think this is probably a really important way to go, but this is a product thing, you know, what can like, for example, a fire safety designer right now designing a building where they know that will be batteries, can they give any recommendations, building some kind of safety in the building, do you think?
I mean, I guess it depends partly on what sort of batteries we're talking about. So if we're talking about sort of large scale batteries for solar panels or something, then I think that when they're on that sort of scale, it's quite possibly a sensible idea to put them in their own fire compartments, maybe with dedicated extract systems, that sort of aspect. I suspect that's all already being done, but that seems sensible for those sorts of things.
I think.
No? Okay.
No, not in small houses, I think. People are not doing that today. But I agree with you that is a good thing to do.
But that sort of thing, I think, is a good idea. When it comes to how do we deal with personal electronics, then it becomes a little bit trickier. But yeah. Good.
Yeah, but I also imagine that all things will be, connected to internet. So in the future, so even small e-bikes and cars and stuff, they will be connected, and then you can have that connected to some alarm system and so on. So it can be really early detection, not by detecting gases and stuff, but there can be a detection before that happens.
Yes. Yeah.
So
but
maybe
if you're
in the future we should have a fire alarm actually connected to the battery management systems, or
yeah, the car can be connected to some central in the building or car park or what it is. I'm just speculating a bit, but why not?
Yeah. And then, but yeah, if you're talking about people now taking their bike batteries into the house to charge, then I think it's a case of, yeah, don't put them right next to your door to get out your front door. Probably better put them somewhere else which you won't block your escape if something does go wrong. But also, yeah, make sure that you've got carbon monoxide and fire detectors in your house. Yeah, they won't provide super early warning, but should hopefully provide enough that if something does go wrong, you're still okay. I think that's the sensible thing to do at the moment.
Yeah, and then what we always talk about, don't use, if it's mechanical damage to the thing, don't use it, and don't, if it's really cheap, maybe not use it, and
yeah, exactly.
Yeah, it's really interesting. We also get a question about extinguishing fire with batteries. If you have a fire in batteries like that, can you put water on it? What will happen? Is it a good thing or a bad thing?
So my understanding is that they are quite hard to extinguish. So it can be good to do water if you have a steady supply. If you're a person and it's your own little laptop battery or it's a electric bike battery, there's no point in you doing it as an individual. But in terms of firefighting, they can do, I think, is it defensive actions that it's called, and you use water can be used for cooling, and it keeps the size of the fire down and can limit its spread, but it probably won't extinguish it, because it's a lot of it's driven by internal chemical reactions more than the heat from the flames and the combustion at the gas, as it meets air, like you would have with a traditional fuel. So it's much more driven by the chemical reactions going on in the battery itself, which are much harder to then stop with just water. So I think my understanding is that it's quite typical to do, I think it's defensive firefighting it's called, where you're cooling the site and the surroundings to limit spread rather than to directly extinguish.
But lithium-ion batteries are not. It's not a danger to put water.
I don't believe so. Not like, a live electric current somewhere, from your mains sort of fire, not or like a cooking fire with oil. So it's not going to do that.
Right.
But firefighters will know better than me.
Okay. Well, if you turn the fire scenario around, let's say the fire starts in a room where you have a battery like this, will it withstand the fire, or will it get involved and get a thermal runaway later on? What do you think?
So you mean you have a room fire and you have an?
And you have a battery in that room that is not affected in the starting.
I think it will be involved quite soon.
Yeah.
It will be, yeah.
And make everything worse.
Yeah. Okay. Thank you.
So I'm sorry to say, but
Bad news. Well, I have a question for you, Vasudev. When we have those things in our regular homes, do we need to upgrade our electrical systems in general to limit the risk of short circuits near the batteries, or do they protect themselves usually?
What do you mean by upgrade electrical systems? Is it
well, in my building, for example, is a short circuit in the building? Is that a risk for the battery if it is at charge, or is a short circuit only a risk if it happens in the battery's system itself?
I would definitely say it's the latter, because generally, if you're, for example, just charging a battery system at your home and there is a problem in the electrical network within the building or something else goes off, then in most cases, at least in current times, there is enough of safety already inbuilt in these systems to just strip the mains or just cut off power to the segments that has a problem. So at least as long as it is pertaining to problems related to a battery, I would say that it's a problem if there is a short within the battery and not if it's something else and a battery is just connected to the grid. That should, there are so many layers of protection. There are passive protection devices like fuses that is not only on a module level, but also for every single cell, especially if they are cylindrical cells or prismatic cells. Each cell has a fuse of its own. Usually there shouldn't be a problem at all unless there is an electrical short which is causing a big fire. Then it's like what we discussed before. There is fire and then there's battery in its proximity. Then maybe it's a different situation, but otherwise it shouldn't generally be a problem.
Okay, thank you. So if we look forward now, what's your next step? Do you think? What would you like to do tomorrow about this new knowledge and moving on forward?
Anyone?
Yeah, I think it's for sure. I think for the battery fire is one of the challenges that is very limited knowledge in the fire community today because of different battery chemistry, state of charge, and they have a very different composition of the gas from the batteries. And that we have not so much knowledge about what kind of battery fire will look like in combination with these battery storage systems. And also, about this, how to extinguish, as Johan mentioned, how to extinguish the battery fires. And it's our current projects showed that it's very difficult to extinguish the battery fire from the outside. And there is very limited designs that allow the cooling, the fire extinguish channels inside the battery pack. And this is a challenge to cool down the batteries when it becomes hot. And also challenges around performing the test with very multiple tests with very high cost, and how can we reduce the cost by combine the experiments with simulations. That is also done in a very limited cases. Yeah, so maybe.
Yeah, no, I agree with Shen. I think the next sort of key aspects, whether it's us or whether it's other people, is sort of building up a bigger knowledge base of the individual cell type gas releases, how these different things propagate between each other. So we've got essentially it's like building up a set of design fires, but it's not just fires, it's gas releases, it's cell chemistry, it's all these things that are then can be used by engineers designing buildings to understand how these different aspects might affect their building, and do they need to change where they do any changes to sort of fire separation or ventilation or anything like that, but also for designers to then be able to investigate a little bit more easily restriction methods for restricting thermal runaway or propagation, or these aspects in the batteries themselves. But a lot of it is currently, as Steve said, it's quite hard to find a lot of the data for these different systems in literature. Where it has been done, it's quite often behind commercial sort of not knowledge walls, as it were. The companies keep their own data and their own testing in-house, and it means that as a wider community, it can be very hard to get a good grip on the overall picture. These things, and I think it's building up that base set of knowledge that's the real key.
Yeah. Is there any international standards so far that they need to comply to, or in terms of safety and so forth?
I think there's a lot of different electrical ones in terms of the electrical design of the batteries, and yeah. But in terms of fire safety style regulations, as far as I'm aware, there's not so many specific regulations worldwide where they are capturing batteries as a separate risk that needs to be mitigated in its own particular special ways, as opposed to just being captured in the same way along with your other fire risks. So yeah, maybe that's somewhere which we need to catch up, but before we can fully establish how that should be done, we need that base set of knowledge first, I think. Yeah, sounds wise. Yes. So before looking ahead again, Johan and Vasudev, we also get a question here about lightning. If a lightning strikes your car or your building where you have batteries on charge, can they be affected?
Well, in theory, not, because most of the buildings, also if they're any higher than a certain height, I think they usually have these things called lightning arresters, whose whole job is so that if a lightning hits the building, it's basically a metal spike that's jutting out of the top of the building, and then it is grounded with certain standards. So you basically find a shortest path for the lightning to go through into the ground, and so that it doesn't disrupt things inside the building. And also, I think, like I said, with so much of technology and standards and all of that developing, we see this in almost all places. It's really rare to see buildings being destroyed because of lightnings, for example, at least in this age. And for cars, it's a little different, but it should still not be a problem because the car basically acts like a Faraday cage. Yeah. So I think if there is a lightning and you're next to a car, the safest place is to be inside the car, and because it's a big conductor and the lightning finds the easiest path that is on the surface of the car, and then it goes into the ground because it's easy to jump over to the ground. So I would say that since the battery pack is inside the car, it would still be the same, that it would make no difference to the battery pack. But it's a very interesting question, and I haven't come across a situation, or I haven't read anything about anything in the news or articles about an electric vehicle being hit by a lightning, and if it has had any bad effects. I'm not really sure if I want to see that in the news, but
maybe in a research project.
Yeah, absolutely.
So if I may add, I mean, it's a regular problem for aircraft. If you talk about commercial airliners, right, they get regularly hit by lightning, and it doesn't happen anything because they are designed that way, and because it's a big Faraday cage, basically. So it would be the same with a car.
Right. Okay. Thank you.
So in theory, at least, not much would happen. In
theory, at least, yes. Well, thank you. Anything else before we wrap out? Any more looking ahead?
From an electrical standpoint, I think, like we mentioned, it would be really nice to also integrate battery management systems into such work to see if this added layer of security can be improved, how it has an effect on these fires, if there's an early detection, and if on one step ahead, if it can be integrated with the safety systems of the building, for instance, like Johan mentioned, if there can be alarms that is raised in the safety of the building that is coming from the BMS of the different storage units. Maybe that would be an interesting thing to evaluate or look into as well.
Yeah.
So in short, I think we are planning for future projects in different areas here. So
yeah, sounds really good. I think I'm looking forward to that. So thank all of you. It's been very interesting to learn more about batteries. Well, thank you very much. I will try to just wrap up and with a short information about our upcoming webinars. So yes, and of course, I always like to mention our fundraising. It's still open for this year, and it's also open for next year's, of course. So please chip in if you like to, if you're not doing that already, and if you are, thank you very much. We have more upcoming webinars this fall. The next one is in 1 week from today. You can always get news about our webinars if you have our newsletter. You apply to that in the bottom field at our webpage, and you can also follow us on LinkedIn and other social media. If you want to see webinars that we've been doing before this one, you can see it on the webpage or on our YouTube channel. And if you have any suggestions on webinars that you wish that we can do, please contact us with any suggestions. That's always interesting to hear about what you want to hear about. And of course, I want to thank my colleagues, Francis Eurenius and Matthias Hammarin, that has been producing this webinar. So thank you, researchers, for this very interesting and important research project and your presentation and all the discussions. And thank to all of you listening and asking good questions. And thank to all of you using and spreading our the knowledge that we produce here. It's of course of great importance that you use this knowledge to make the world a safer place. And please answer our questionnaire that will be sent to you after the webinar. And you are of course always welcome to get in contact with us. You find our contact information at the webpage. And thank you very much. Bye-bye.